In this video, I'm going to prove this statement rigorously by recasting it into its epsilon-delta form. So what that means is that I want to show that for whatever kind of epsilon that you can come up with, I can always set the value of delta into a certain value such that if x is within a distance of delta away from 2, then this implies that the corresponding value of x, its x squared, is within a distance of epsilon away from 4. So this is what I need to show in this video. So in order to do this, I'm going to start off with this line. I'm going to start off with x minus 2 being between 0 and delta. And what I would like to show is that for whatever value of epsilon that you can come up with, I can always set delta to be such a value so that this line will imply that x squared minus 4 is smaller than epsilon. So in order to do this, I'm going to multiply each term with a x plus 2. So we have an x plus 2 attached to each term. And then for this middle term, I can just combine the terms inside the absolute value sign. So I get x squared minus 4 is smaller than delta times x plus 2. So now it seems like I need to choose delta to be some certain value so that this term over here will become epsilon. And if I can do that, if I can choose delta to be a certain term so that this term becomes an epsilon, then I would have essentially proved that x minus 2 being smaller than delta would imply that x squared minus 4 is smaller than epsilon, which is what we want to show. So how do we choose this value of delta? What must delta be equal to? So first of all, it seems like we can choose delta to be equal to epsilon divided by x plus 2. But then this is actually not a valid choice because delta has to be a constant. It can't be dependent on on a point that you're considering within the interval. So this choice is actually wrong because there's an x in the denominator. So the question remains, how should we choose delta so that we can construct the epsilon-delta definition? So it seems like in order to choose a value of delta that works, it seems like we must somehow get rid of this x plus 2 term over here. And we can actually do that if we restrict our delta to be always smaller than or equal to 1. Because if we impose this restriction upon our delta, you will see that x minus 2 is always smaller than delta, and in this case we know that it's always smaller than or equal to 1 because I'm going to consider the case that we are going to choose a delta that's always smaller than or equal to 1. And if I do that, you'll see that this implies that x minus 2 must always be smaller than 1. And so this means x minus 2 must always be between negative 1 and positive 1. So that means x must always be between 1 and 3. And so if I add 2 to each one of these terms, you'll see that x plus 2 must always be between 3 and 5. And so you can see that this term over here, this x plus 2 term over here, must always be smaller than 5 if our delta is chosen to be a value, so that it will always be smaller than or equal to 1. So this is a useful outcome that will be useful later on, as I'm about to demonstrate. So now, summarizing the findings we have obtained so far, I'm going to choose a value of delta that is actually going to allow us to construct the epsilon-delta definition. So the value of delta I'm going to choose is going to be equal to the minimum of either 1 or epsilon over 5. So what this means is that if epsilon is small enough, then your delta is just going to be equal to epsilon over 5. And if your epsilon is large, let's say 6 over 5, then your delta is just going to be equal to 1. And then for such a choice, you can see that delta must always be smaller than or equal to 1. Because if epsilon is too large, then you will just take the minimum, which is just 1. So for this expression, delta can never be larger than 1 because of this minimum and because of this 1 over here. And so that means our delta is always smaller than or equal to 1. So that means I can actually use this result over here. Now I know that x plus 2 must lie between 3 and 5. And now I can actually show you that this choice of delta would actually allow us to construct the epsilon-delta definition. So in order to do this, I'm going to break this up into two cases. So the first case is when delta is equal to epsilon over 5. So this would correspond to the case when epsilon is smaller than 5. And there's a second case when delta is equal to 1. And this would be the case when epsilon is larger than or equal to 5. So I'm going to analyze both cases separately. So for this first case, you can see that for whatever epsilon that you choose, I'm going to set delta to be equal to epsilon over 5. And you can see that this statement, x minus 2 smaller than delta, will imply that x squared minus 4 is smaller than x plus 2 times delta. And for this case, epsilon is smaller than 5. You can see that delta must always be smaller than or equal to 1. So this x plus 2 term must always be smaller than 5. And so this term x squared minus 4, which is smaller than x plus 2 times delta, must always be smaller than 5 times delta. And in this case, delta is set to be equal to epsilon over 5. And so that means 5 delta is just equal to 5 times epsilon over 5, which is equal to epsilon. And so this shows that x minus 2 being smaller than delta implies that x squared minus 4 will be smaller than epsilon. And so what this shows is that for whatever value of epsilon that you choose that is smaller than 5, there does indeed exist a value of delta, such that x minus 2 being smaller than delta will imply x squared minus 4 being smaller than epsilon. So essentially we have constructed the epsilon-delta definition for this case. So moving on to the second case, this is actually kind of redundant because I've just shown that the definition works for small values of epsilon, and in that case that means it will definitely work for large values of epsilon, because I can always just choose delta to be equal to the corresponding value for small values of epsilon, and that delta will definitely work for large values of epsilon. So in a sense this is actually kind of redundant. I don't really need to construct a proof for this case, but for the sake of completeness I will still show you how we can construct the conditional statement for this scenario. So we just start off with x minus 2 being smaller than delta, and we know that this implies that x squared minus 4 is smaller than x plus 2 times delta. And since delta is smaller than or equal to 1, that means x plus 2 is smaller than 5, so we have 5 times delta, and the delta in this case is just equal to 1, so we have 5, which we know is always smaller than or equal to epsilon. So what we've just shown is that for whatever value of epsilon that you choose that is larger than or equal to 5, there always exists a value of delta. In this case it's equal to 1, such that x minus 2 being smaller than delta will imply that x squared minus 4 is smaller than epsilon. And so essentially this concludes the proof. We've just shown that for whatever value of epsilon, there will always exist a value of delta, such that x minus 2 being smaller than delta will imply that x squared minus 4 is smaller than epsilon. So this concludes the proof.